while triangle of Hi all, welcome to week 10 lecture. So basically last week we discussed mostly about the singular value decomposition, and also we saw like why we do singular value decomposition because if for normal matrices, if we do eigenvalue decomposition, then we are able to find eigenvalue and eigenvector, and that will give the rotation um around the maximum eigenvalue. So for that purpose, we are calculating this eigenvalue decomposition and also singular value decomposition. So for singular value decomposition, as we know, it can be singular value decomposition is possible for any kind of matrices, rectangular or square, but eigenvalue decomposition was only possible for square matrices. That we knew at that time. So I'm just revisiting week 9 questions. So the questions was sort of easy, and we solved also. So those who don't know week 9 thing, so they can watch in my YouTube channel. Uh, so this was a question that was very important. So that proof is given using this. So I wanted to show you because that's one of the student asked that last time. So let A belongs to R n cross n, and A is equals to U sigma V transpose with the SVD of A, then which of the following is true? So we have to check whether this Frobenius norm uh, is less than or equals to the in 2 norm of matrix and UV transpose. And all so this is yes, because this is given from the theorem. And how we can do, even if you don't know anything, so we should start for the proof, we should start with the given thing. So given thing is A is equals to U sigma V transpose, where sigma is actually the diagonal matrix with ordered singular values, as we know, sigma 1 greater than sigma 2 greater than sigma 3, and so on. So in such scenario, if we replace sigma I with sigma 1, we will get uh, how we will you will get if we replace only sigma 1, so A will be lesser, because anyway we have to prove by less than equals to, right? So A will be less than equals to this U sigma 1, because this is the diagonal, so we can write by multiplying by I, so V transpose. So if you do that, so this particular equation implies Frobenius norm of A less than equals to sigma 1 UV transpose Frobenius norm of F. So basically, as we know, the norms are basically defined for a vector. But if you define for a matrix, then that norm will be for all the elements of the matrix. So in that case, whether it is 2 norm or 3 norm or 4 norm or infinity norm or Frobenius norm itself. So we need to define for all the elements. So as we know, the Frobenius norm is nothing but a f is equals to root over summation of all a I squares, where ij belongs to mn, number of columns and number of rows. So this can also be written as root over trace of A transpose A. Okay, so this matrix is very important, which is also called gram matrix. So, as we know, this gram matrix is always orthogonal. So, orthogonal matrix have some properties, like the norm will not change after multiplication of the orthogonal matrix, and the columns of the orthogonal matrix as a constant. So that's why it is written in this form. So can anyone tell me how two norm of any matrix can be written in terms of this? So it is basically, yes, basically lambda max A transpose A. So last time we had some doubt over it. This is not this. So this is the last time notes. So this is wrong here. So I would like to correct it here. So norm is actually root over lambda max. So it is a max of A transpose A. Oh, this is it. Also, we know that can be written as maximum magnitude of A, maximum magnification of A, minimum max magnification of A, minimum magnification of A. So that we will take care from the sensitivity analysis. So yeah, so I think we can move to the uh, week 10 lecture. So basically, as we know, this A can be written as U sigma V transpose, where for any matrix that the rectangular matrix, this is M, not necessary to be equals to N. There exists a orthogonal matrix U and V and diagonal like matrix sigma with these elements, and this up to rank R. On the principal diagonal are not equals to rank of A, so A is actually U sigma V transpose. So AV is equals to U sigma. Okay, so AVI is equals to sigma IUI. You can write like A is equals to, if you keep that this VI as VI inverse here, so that inverse is equals to transpose, because all those things are in orthogonal matrices. Basically, and if you want to write V, so V is what? Eigenvectors of, I hope you remember, A transpose A. U is what? Eigenvectors of U, sorry, A transpose. Hmm? And if you want to write like this, so here you observe these are all rank 1 matrices. Okay, so if you want to write A is equals to, that is a data matrix. So that here we are coming to the principal component analysis. So if we have the data matrix that is spread around the 3D, then how can you do the principal component analysis? Okay, so if A is equals to A1 transpose, A2 transpose till AM transpose, that is belongs to R M cross N. So if M is the number of rows, number of data points, and each data point. So basically what we are trying to do here, we are stacking every data point one by one. So every data point has one separate features, that is a column that can be written as the column vector. Okay, so here what happens, so suppose you want to determine the price of a house. Okay, so you will have the data around you. So data can be what are the features of house? The house have 4 bedrooms, 3 bedrooms, or one toilets, or one whether it has interior or not. So these are some of the features. Suppose 5 features of the house are there, but how many houses are there? So the number of houses are actually the data points. The number of features is n. So here the number of m rows is the number of data points. So if you see the handwritten MNIST dataset, you can go to the Kaggle website and you can see the dataset. So you will have the 60,000 images with M. So you can write like this, where each image is of the vector 28 cross 28. Okay, so what happens if you want to project these images into the lines, so a 2D or 3D. So in that case, you have to project all the data sets into 2D. The number of the variance around it. Okay, you want to know that. So in that case, we do the principal component analysis, and how we do. So we can do using SVD also. So we will first see how can we do without SVD, and then we will see how can we incorporate SVD into it. Okay. So suppose A tilde is actually the data point 817, 8, 17, 1, 4, 12, 18, 6, 9. So these are some data points here you can see. So if first of all, the feature engineering is to have, you have to keep all the data into mean centered. Okay. And then variance covariance matrix. So this is A transpose A. So this is a variance covariance matrix. So here also you can see this graph matrix is using here. So if you want to do, so here this is a direction, one direction that is you can call is as a V1. The other direction is perpendicular to this, you can call is a V2. Okay, so the variance covariance matrix is A transpose A divided by M minus 1. So A transpose A is actually A1 transpose till AM transpose. Say A transpose, this will be the A transpose, and this is the A. So this 2 cross 2 in our case. just taking the example. So this A transpose is what's giving it. Just see this. This is the variance of F1. So this is A1 transpose A1. This is variance of F1. Okay. Covariance of F1, F2 is what? You can just solve this. This is A1 transpose. This is AM transpose. This is A1 transpose. This is AM transpose. So here you can see if it is actually this A1 is a, so here it will be N cross M, and this is will be M cross N. So you are getting as N cross M. This is the data point because A1 is actually the vector of length M. Uh, because any data will have the all the features. So if you see this A1 transpose A1, and then this will goes on AM transpose AM. This all will be sum. Okay. So this particular matrix is this. And this first one is variance of first F1. This variance of F1, F2. This way covariance of F1, F2. This is a variance of F2. So this gram matrix is actually giving you variance. That is uh, good to see. Okay. Now moving ahead, this A is equals to this if we stack in this particular matrix as A1, A2, An, where A1 is actually a vector of size n because it is having the n features. Okay, so for any orthogonal matrix, so as we know, the multiplication of the orthogonal matrix doesn't change the norm of the matrix. So if you multiply with the orthogonal matrix V, suppose, so we are equating it with respect to A and AV, Frobenius norm, because any norm of a matrix, so you can also consider the Frobenius norm, because for norm matrix, the general norm considered is actually the Frobenius norm. Okay, so uh, yeah, so here you can see in the picture this mod of AM A transpose is equals to this particular thing. This is going, so sorry, this is going this term and this term. How it is? Because if you multiply this V1 and V2, so this is going AI term. Every column will be multiplied by V1 and V2. Okay, so this is giving you this. So now, since principal component analysis wants one particular vector to be more in one particular vector to be very less. So what we do, we are maximizing with respect to one particular direction. So we are maximizing with suppose with respect to V1. So if we can see here, this is a V1 direction of V1. So if you maximize with respect to V1, so automatically this will be minimized. The green color will be minimized. Okay. So as we know, this particular thing is fixed given the data matrix. So how will you minimize it? Okay. So now if you can write like this here, this is A transpose A. So this is what AV transpose AV. Okay. So this is giving you V transpose AV, because this matrix, this is equals to this. Okay. 1 to M AI transpose V. Okay. So, if you do this AB transpose AV, so it is giving you this, and this particular thing is actually called the Rayleigh quotient. Okay, so we are maximizing the Rayleigh quotient in principal component analysis. So that is a good thing to know here. And this particular matrix is actually the Gram matrix. That is again a orthogonal matrix. So, how to maximize it? So, if lambda 1 or lambda are a sigma 1 square, because actually lambda the eigenvalue is equals to the singular value coefficient square. So, be the largest eigenvalue of A transpose A, then the eigenvector, obviously, this will be the eigenvector of E1. Okay, so this will be the maximum. So, this maximum is giving you direction of maximum eigenvalue. value. So as we know, so any function is concentrated around a direction that is a eigenvector, and the scaling factor that it either shrinks or expands is eigenvalue. So if the direction is along the maximum eigenvalues, so it will be corresponding to the maximum eigenvector. Okay, eigenvector corresponding to maximum eigenvalue. So here, this if v1 is actually the one principal component, then v2 will be the second eigenvector. Okay, so here you can observe the lambda 1 is the eigenvalue corresponding to v1, and lambda 2 is the eigenvector corresponding to v2. Okay, where v1, v2 are the first eigenvector and second eigenvector, and these are also called principal components. So we are projecting the overall data into these two eigenvectors. Okay, so first we are plotting the data, and then we are checking the maximum variance direction. So first eigenvector is the maximum variance direction, and the second one is actually the perpendicular one. Okay, second one is actually a perpendicular one. So we are minimizing the difference of the orthogonal magnitudes, but at the same time we are projecting the all the data set around the one axis. This is called principal component analysis. Now you may wonder, what is the difference between principal component analysis and least square? So in least square, what we used to do, we used to find the solution of a triangular matrix, either triangular matrix, sorry, rectangular matrix, that is a tall. Okay, again reminding tall. But it is not for wide matrices. Then either square matrices. So in that case, whenever the unique solution doesn't exist, so approximate solution we used to find. So we we were minimizing the error between the actual projection with respect to the approximate values. Okay, so in that case, what is the difference between these two? Can anyone tell me? Dr. Sri Sharana, I'm seeing you for the first time in my class. Can you please, how many lectures you have watched? I'm waiting for your response. Okay, so going back, so as we know, the what is the difference between these two things? Principal component analysis and not. So here also this mod of AF square is actually the trace of A transpose A, an assumption where columns are mean centered, and these are the variance. Okay, and if you write, you can write this A matrix as a term of K dimensional subspace U V transpose. Okay, so A is equals to 3, 7 minus 4, if you can write like this. So direction of V1 is this, and direction of V2 is this. So this A transpose A divided by M minus 1. Okay. So if we can calculate the eigenvalue, so eigenvalue is this one, where the vector is this one, where the eigenvalue for the other vector is actually the 3.5, the corresponding eigenvector you can calculate. So this particular matrix, that is zero point 0.6 and zero point 0.8. So if this zero point 0.6 and zero point 0.8 is actually the principal component, this one is also the principal component. So two principal components. Now, note of caution. This is important sort of thing. So, what is the difference between these two? So, this is the first thing, the principal component analysis. Second one is the least square. So, first, the principal component analysis is actually taking the orthogonal distance from the line. So, we are drawing one line. And then we are taking the orthogonal distance, and this particular direction is v2, and this particular direction is v1. Whereas here in least square, we are taking the vertical distance from the line. So this vertical distance and the orthogonal distance is different. I hope this is clear. This is least squares. So yeah, if A belongs to R m cross n, and this minimum, and we are taking this example of least squares. If minimum of ax minus b norm of this thing, then if A is having linear independent columns, the least square problem has a unique solution, as we know. Okay, but what if it doesn't have? In that case, what will we do? What will we do? Okay, so here we will approximate with respect to singular value decomposition. Okay, if A belongs to R n cross n and invertible, if A we can write like this, then SVD of this one is this, and this is this, as we know from the SVD. If you do the A inverse, hmm, so A inverse can be directly calculated by switching this V here and U transport here, and sigma inverse. Okay. Now, if you project one column space to another, so how will it look like? Give me 2 seconds. So yes, if we project from R to Rn, and if we do the A inverse, so definitely if V1 is transposed to one range space to one column space, that is V1 is giving to U, and then again if you do the inverse, so it will give you V. That is there. Okay, so here T where Rn to Rn, and T is non-invertible here, so the sigma 1 to sigma R is actually greater than 0, and R is the rank of a matrix, so this T is U sigma V transpose. Okay, so if Rn, this is V1 V2 to Vr, and if it is belong to null space of transpose, so as we know the null space of a matrix is perpendicular to column space. Okay, and if we see the null space of A transpose is perpendicular to row space. So row space, what do I mean by row space? The range space of A transpose is actually the row space, and range space of A is actually column space. Hmm? Okay, so if you go T span of V1 to VR to span of U1 to UR, so if we just we're taking a transformation of this, so you may wonder how, I'm not sure whether you're getting or not, but yeah, I hope this you got. A V is equals to U sigma. Okay, so this V is acting on A, and we're getting as U, because sigma is just a constant. You can keep as like this. But similarly, A inverse U is actually giving you V sigma inverse. Okay, so now if you got this particular thing and you're acting A inverse on it, you're getting V. That is strange, right? So yeah, this particular thing we can map it as a transformation. And then if we can write like uh, this particular matrix T, how will it look? Waiting for response. X inverse AX. Okay, and or you can write A is equals to X inverse. So this is actually what we are talking about. Okay, X plus X have so many eigenvectors. For one eigenvector, you have uh, star is equal to, yeah. So transformation is a problem, right? So I have discussed in my lecture, because taking the same things again is doesn't make any sense. So yeah, previous week to week I have uploaded. So you can see that. Hmm? Week 8. I was just checking my videos only. So week 8. Ah yeah, sure. Yes, yes. You can mail me. That's fine. So I think this is a week 10. So two more classes we will have, week 11 and week 12. And also we will also have one extra session. So I have applied for. So in that extra session, I will take care all the problems that you have faced. If we see the present uh, assignments, you're talking about present assignments. Uh, that I don't. Yeah, so sorry. Okay, so moving ahead, why this transformation is there, I hope you understood. Okay, so what I'm trying to do here is the first question. Okay, that yeah. So I want to write the transformation actually. Okay, so here the span of U is V is mapped to span of U. So how this is mapped? This is mapped using this particular two equations, 1 and 2. Now you may wonder how can we write this T? So T is nothing but U sigma V transpose, and how can we write Q? That's great. Okay, so in order to write this Q is nothing but V sigma plus this is still, so plus is actually pseudo inverse, so this v u transpose. Okay, so what we're trying to do here, this A is equals to U sigma V transpose, where SBD of A sigma 1 sigma this things. So at the end, using A inverse we are getting the same values. So this transformation is actually what, inversible, irreducible, what we can say in terms of Markov chain. So this Markov chain thing will also come in the next class next week. The that I will be interested to take care. Okay. Uh, so I hope this is clear. This A sigma is actually this construct, because uh, if we can write this A is equals to U sigma V transpose. So A plus or A inverse. How can we write this? V sigma plus U transpose, where sigma plus is actually 1 by lambda sigma 1, 1 by sigma 2, so on. Okay, this is 0. So what does this mean? So if A is just m cross n and m is greater than n, and the columns of A are linearly independent, so SVD, what does this giving? If A can be written as U sigma V transpose, and A transpose equals to V sigma transpose U transpose, and A transpose A, if you can write like this. So as we know, this A transpose A is nothing but V sigma plus uh, sigma transpose sigma V transpose, and if you can write like this is V, this is inverse. So SPD of A, you can write, this is also equals to this V sigma transpose U transpose, and so that's great if we can equate the pseudo inverses A transpose A whole inverse A transpose as V sigma plus U transpose. So if we can equate this, because anyway, if we prove it, this particular thing with this particular thing, that is equal. So find x belongs to our operand such that x minimizes this x ax minus b whole square. So we have to recall that A has linearly independent columns. This means there exists a unique least square solution given by A transpose A whole inverse A transpose into B. So now, if we don't put any restriction on M and N and no condition on linearly independent, so it can be wide, it can be anything. Okay, that's great. Okay, now how can we, in case of non-unique solution, we will seek the least square solution x with minimum norm. Okay, so if we have to replace with the minimum norm, uh, the minimum norm will be then if we can write like this, mod of x2, this is minimum of x uh, belongs to y belongs to our mod n. So any guesses till now? Any guesses? What will the solution? So if we just put this values ax minus b whole 2 norm square. So u sigma v transpose x minus b, and if we keep u transpose as out, using singular value decomposition, we are not keeping any restrictions on a and this m and n. So now we are trying to get the values. Okay. And if you keep V transpose X as Y and U transpose be as C, so if A, let the A be of rank R. Sorry. So sigma Y1 minus C, sigma Y2 minus C, 2, and if we keep it like this, so minimizing with respect to S is same as minimizing the sum of square in RHS with respect to Y. Okay. So here we note that only Y1, Y2, to YR take part in minimizing the residual, whereas which are other part of the rank will be free. So y1 is equals to c1 by sigma 1, y2 is equals to c2 by sigma 2, yr is equals to cr by sigma r. So this particular thing is minimizing this, which is ax is equals to b. So the minimum norm solution of this is actually the same as minimum norm solution of this one. So the sigma is this thing. So what is the answer that you're getting? So if we go through the solutions, so sorry, the explanation or the derivation, that derivation may vary from person to person. So you can also leave that derivation as far as I know, but yeah, you try to replicate it by your own derivations and all. So that's wanted. So if y is equals to y tilde z where y tilde belongs to r power r, where z should belong to n minus r, definitely. So this x belongs to r power n be the least norm solution of this particular thing. So minimum of x belongs to r power n such that ax minus b 2 norm square is less. I hope this is clear. So if x is equals to vy, v this particular thing. So if a belongs to a r m cross n and b belongs to r power m, be given, let x be the least norms least square solution to a is equals to b. So here you are getting the same answer. So here a when columns of a are linearly independent, okay, and when wait a second. A belongs to R m cross n, B belongs to R power n. Minimum of ax minus b whole square. If A is having the linear independent order, the least square of the unique solution. If A is invertible, SVD of this one. So what I'm trying to tell. So if it is not least square, okay. So in that case, A plus is actually what? A plus was U sigma plus V transpose. So in case of non-linear independent columns, this is A plus B. Or in case of linear independent column, this will be A plus will be equals to A transpose A whole inverse A transpose. Okay, so you are getting in the same form A plus B, but in both cases, A plus is different. I hope this is clear. How this is possible? You may wonder. Anyway, because the transformation that we are taking care is from A and A inverse. Okay, from that perspective. Again, we went back. What is there? Now the sensitivity analysis. Can you read this once? Because sensitivity analysis was a bit easy. We talked a lot about this sensitivity analysis in lecture 6. Okay, so in fact, sir also explained it well. But yeah, we can revise it and we can recapitulate it. So if A belongs to R n cross n and it is invertible, and B belongs to R cross R power n, so we have to compute x such that Ax is equals to B. So if B is tending to B plus uh, delta P, then how much sensitive uh, x will be? Okay, so this was given by the k2 of a. This is a maximum magnitude of a and divided by minimum magnitude of a. That is given as again recapitulating it. So if you perturb any element, so how the perturbation will be happening at the RHS also. So that is there. So del x by x, the perturbation in x. Okay, after perturbing the uh, b, so it is less than equals to k2 of a mod of del b by mod of b. So k2 of a is maximum magnitude of a divided by minimum magnitude of a, that is given as that is equal to mod of 2 norm of 2 multiplied by 2 norm of a inverse. So that is the case, and it is equal to sigma 1 divided by sigma n. Okay, why this is sigma 1 and sigma n? Because the maximum magnitude of A will be given by sigma 1, whereas minimum magnitude of A will be given by sigma n. So that is why. As we know, if you remember, this sigma was actually sigma 1, sigma 2, to sigma r. N is actually 0. So here n should be sigma r, where r is the rank of a matrix, because anyway, that will be 0. So you can't divide by 0. So this is sigma 1 divided sigma r, where sigma 1 is the maximum singular value in the matrix, and sigma r is the minimum one. Okay, so this is the case. It should be less than the 2 norm of A multiplied by 2 norm of A inverse. So what is the 2 norm of A? As I told, that will be here also we can see. Uh, so this K2 of A, K2 of A is 2 norm of A multiplied by 2 norm of A inverse. Okay, this 2 norm was root over lambda max of A transpose A, and this is also divided by, it will be 2 because it will be inverse. Okay, so either you multiply here or you multiply by inverse here. So lambda max A transpose A, because if you do the eigenvalue of A is lambda, what will the eigenvalue of A inverse? 1 by lambda. Okay, so same goes here. So that is given by sigma 1 divided by sigma r. I hope this is clear. So if we do the sensitivity analysis of least square problem using SVD, so that is there. Sensitivity analysis of least square problem where A belongs to R, M cross N, and B belongs to uh, this R power M. So if you perturb B, so what will be the perturbation on X? So any guesses? Any guesses? So if we do the geometric interpretation and then we will analyze. Okay, so if this is a range space of A, where what is the range space first? All the linear combination of the columns of a matrix will be the range space of A. Okay, that is fine. Sometimes whenever we do the analysis, we should question ourselves like, what is this? And if you don't know, then we can Google or ChatGPT or whatever. So this, if y is equals to ax plus b here, and if we plot b, so this particular thing is actually the residual. Hmm? And this y, all the y that you're getting, okay, that will be the range space of A. Ax is equals to b. So sorry, ax is equals to b. So ax minus b, because y is equals to ax here, ax minus b is actually the residual. So column space of A is the range space of A. If B doesn't belong to our range space of A, then the solution will not exist. Okay, that's why the uh, residual thing is coming into the picture. So if we do the geometric interpretation and B is outside of the column space, okay, as we can see here. So if y is equals to A, so this mod of R, this is mod of AX is equals to B cos theta. So if we do perturb this B, So it is, if it is projected on a range space of A, so Y will be projection of B plus delta B. That is for sure. So delta Y may be very large in that case. So in that case, the sensitivity analysis is very important. Okay, because Y is actually the projection of B on a range space of A. Okay, so even if the Y delta Y is small, this A x multiply by x plus delta x can be very high. Okay, that will maybe causing to the L condition criteria. So this implies this is large. So if you go by the normal equation, so as we know, this K2 of A is nothing but, again I'm reminding because I also want to remember, maximum magnitude of A divided by minimum magnitude of A. That was sigma 1 by sigma 2. Because here the A2 of A, why we are multiplying with A? Because we are calculating on B if X is per term. Okay. So normal equation is A transpose A X. My battery is dead. I'll switch off the camera. Hmm. So A transpose A X is equals to A transpose B if it is a normal equation. Okay, just multiplying with the A transpose both the sides. So this least square solution corresponding to the AW will be equals to B plus delta B, and A transpose A is X plus delta X is equals to A transpose into B plus delta B. Okay. So if E has a linear independent columns, so A transpose A X multiplied plus A transpose A multiplied delta X will be this one. Okay, so here also we can see delta X is less than or equals to 1 by sigma n delta B. And if you put all these things, so you're getting it is less than or equals to this particular thing divided by 1 minus 1 by cos theta. So cos theta is important here. So cos theta was what? Cos theta is here, this theta between B and y is equals to ax. So this cos theta is actually causing the extra factor here. So if cos theta is not equals, theta is not equals to pi by 2, so obviously the cos theta is not equal to 1. Okay. So if A is equals to R m cross n, assume that A has n linearly independent eigenvectors v1, v2 to vn, and so if lambda 1 lambda 2 is greater than this particular thing, so here the power method comes to the picture. So if q not equal to 0, be any vector in R power n, and lambda 1 with a dominant eigenvalue and v1 is a dominant eigenvector. So q a square q, if you do this and if you sum this c1 v1 plus c2 v2 so on cn vn, so this particular thing is giving you a lambda 1 power j. Finally you're getting the values as each iteration, the distance reduces roughly by lambda 2 by lambda 1. So if you do the linear convergence, these are some proofs that matrix vector multiplication, if the power iteration runs for m iteration, this is giving you 2 n square m uh, q0 q1 every iteration a matrix vector multiplication. Okay.
You're not audible.
So, okay, we will go to the question sections. Already joined. So, the last page was the answer for this question. So, there is a derivation involved in this. How many number of blobs are required to compute Qn? So, if A belongs to Rn cross n, and if Qi belongs to using the power method, and if Qi is equals to A power I Q naught, so how many number of blobs are required to compute Qn? So, that was there 2m square n m square n. So that's why applying the power iteration for any iteration will result in this one. So one step of our iteration requires m square multiplication and n square addition. So resulting in 2m square flops. Okay. So if you are doing for n iterations, so 2m square n. So even if you want to go, so that is complete derivation. You can look into it. That's not a big deal. So that's why I did not go very deep into it. But yeah, so one thing to note is if each iteration the distance is actually reducing by lambda 2 by lambda 1. So here basically the eigenvalue plays a role here. So that's there. Lambda 1 power j c1 v1 plus c2 lambda 2 by lambda 1 lambda n by lambda 1. Okay, this is important. Okay, so if we lambda 1 is actually dominant eigenvalue and v1 is dominant eigenvector, so what we are trying to do here, that's important. So before sensitivity analysis, what we saw, uh, the sensitivity analysis is giving you 1 by cos theta into the equation was okay. So 1 by cos theta was the equation, which theta was if it is not equals to pi by 2, definitely this 1 by cos theta will be the term here. So, but if you have, this was the equation, okay? So, if you assume the A has linearly independent eigenvectors and eigenvalues, corresponding eigenvalues, so power method is what? If Q is not equal to 0, be any vector in R power n. So if we need to consider Q A square Q till A power I Q. Okay. So, but make sure that we know these things, eigenvalues and eigenvectors. So if you write Q as C1 V1 plus C2 V2 plus so on Cn Vn, the linear combination of the uh, eigenvectors. Okay, so AQ is uh, this particular thing. This is giving this, and A square Q is this one. So what we can see here, the only lambda power is only multiplied here. Okay, otherwise it is same because this Q, why we take care only as a linear combination of the columns of the elements? Because this Q, as we know, the column space of the ring space of A, which we call like this. So this linear combination of the columns of the eigenvectors will definitely be any vector here. So it will belong to range space of A. So this Q is belong to range space of A, which is a column space also. Range space of this interchangeably used as a column space. That is fine. So if you see here, if you take lambda 1 power j out, so this one is c1 v1 c2 lambda 2 power uh, lambda 2 by lambda 1 power j cn lambda n power divided by lambda 1 power j bn. So as j tends to infinity, so the convergence was the convergence states. So convergence states that at the end each direction the distance is reducing by roughly by this lambda 2 by lambda 1. The linear convergence states that it will converge. So it will converge to C1 V1 only because anyway this will goes to 0. This will also goes to 0. Okay, because this lambda 2 by lambda 1 is less than 1. The lambda 3 by lambda 1 is also less than 1. So you are converging to C1 V1. Okay, mm, to one eigenvalue, one eigenvalue vector. Okay, so this is the actual equations. So at each iteration it is reduced by lambda 2 by lambda 1. One thing that we need to take care, say every iteration of matrix vector multiplication is required, because this q naught is there, then a q naught, a q naught, and this one. So this a q naught is required 2n square flops, and if you are doing it for m number of times, m iteration to n square m. So this is 2n square m. I hope that is clear. So that's why the answer is 2m square m. Okay. What is the power iteration method used for this deletion part? Yeah, Ravi, you can watch the recording part, because we cannot go back the same thing. But I can tell like what is this power iteration method used for, and this is actually this particular week was basically on the derivation. Initially, it was very good, like why how singular value decomposition is used for least square solutions, and where we were not keeping any restrictions on the least square on A, because while calculating the least square, what is the difference? The least square is only gives a unique solution when the columns of the matrix is linearly independent. Also, it can be used only for the square matrix as well as tall matrix. But in using syllabary decomposition, we saw in this lecture that we can also use it for the normal matrix, irrespective of the fact that we don't need to keep the condition on the linear independence on the columns. We saw that, and as also we saw the principal component analysis using singular value decomposition, using this gram matrix A transpose A, and we saw that any data matrix can be decomposed into a two-dimensional, three-dimensional principal components. That is that is what gives the essence of the linear algebra, where the one of the vector will be the eigenvector, other vector will also be the eigenvector. So if two-dimension principal component analysis is asked, then two the eigenvectors will be there. So we have to maximize the variance around the one particular axis, whereas minimizing the variance around the two other axes. So that is what the principal component analysis was. But what is the difference between principal component analysis and the least square? We saw that. So if you can go through the lectures, I think that will be there. Okay. So what is the power iteration method used for? So is it used for solving linear system of equations? That we can use it for Ax is equals to b? I think that is no. Is it used for finding the inverse of a matrix? No. For finding the inverse of the matrix, what are the things that we used till cover till time? We use the LU decomposition, we use the QR decomposition, okay, and then we also use either if we can write in the rank one matrix form, A transpose like that. Uh, but now. This power iteration method is not used for that. So is it used for comparing the dominant eigenvalue and corresponding eigenvector of a matrix if it exists? Yes, because that was giving you lambda 2 by lambda 1, okay, plus c1 v1 multiplied by some factors. This was decreasing by this. So yes, this is used for this. This is not used for singular value decomposition. So I think answer is C only. Follows on the definition of power iteration method. Okay, so most of the problems are based on power iteration only. This thing. Okay. So we know that lambda 1 by lambda 2 mod is less than 1. So I think answer will be B. So let's see. If lambda 1, lambda 2, lambda n denotes the eigenvalues of this matrix, where this lambda 1, lambda 2 is this one. It's applying the power iteration method might lead to slow convergence. When? Acha, this is giving you to high convergence. Okay. But uh, if it is giving you high convergence. So if lambda 1 is actually 1, so 1 by lambda 2, it doesn't affect lambda 1 minus zeta is very small quantity. It is also not the case. So answer is D. Okay. YD. So this type of theoretical problems, meaning to the working principle of our iteration method is that with more iterations, the largest eigenvalue becomes the argument dominant. Okay. Also, we saw that only that component, component was only there. Okay. So if lambda one is actually very less, then more iteration will be required. Okay. Okay. So it is asked. Uh, which scenario will require the more iteration, that is giving you the more slow convergence. So the dominant eigenvalue should not be only higher than little by little amount. It should be higher than very much. It should be the case. This should be the case. Okay, this should be very very much. But if it is only greater than very small quantity, then it will require a more number of iterations. So that is giving you slow convergence. So this type of theoretical problems, so these are actually marks gaining for you guys in the exam. That will be very. So this is based on the sensitivity analysis. So consider the least square problems corresponding to x is equals to b, where a belongs to R n cross n, x belongs to R power n, b belongs to R power n, where m is greater than n. So here it is a rectangular matrix. So also assume that the condition number of a is small. Okay, so let us assume that B is perturbed to B plus delta B, where delta B is small, and the angle between the range space of A is also small. Okay, in such case, how will the least square solution be perturbed with this change? Okay, so sorry, we know that delta x by uh, x. Okay, so delta x by x is less than equals to k2 of A 1 by cos theta delta B by del B. Okay, here this is sensitivity analysis, and this K2 is what? Condition number. Okay. And so what is saying, the condition number is A is small. Okay, this is small. That what is the ideal value of condition number? Ideal value is 1. Okay, and when it is a case for ideal value, orthogonal matrix. That's why uh, we always try to convert this. Okay, so anyway, here it is not orthogonal. Instead it is a rectangular matrix. Okay, that's fine. So if the condition number of A is given by 2 norm of A multiplied by 2 norm of A inverse. Okay, that is equals to maximum. Okay, I'm writing it here. K2 of A. Because from sensitivity analysis, you will definitely get 3-4 problems. I'm damn sure about it. Uh, this is 2 norm of A multiplied by 2 norm of A inverse. This is equals to sigma 1 by sigma n using SVD, and this is equals to uh, maximum magnitude of A divided by minimum magnitude of A. Okay, that we saw. Okay, now if cos theta, so if theta is small, okay, so cos will be high. So if cos will be high, so 1 by cos will be low. So this will be, this affects how it will be affecting. It is impossible to predict how it will be changed. It will be changed by small amount. So since this is also small, this is also small. So it will be affecting by small amount only. By I'm telling, this is small as they have told, and if cos theta is small, so cos will be affecting. It will be more. This is more, the 1 by more will be less. So these two, less into less, is actually less. So it is affecting only small quantity. This is equals to small quantity. So that's why this is giving you small quantity. Yeah, same thing only. Looking at the sensitivity analysis formula, this is the condition number. We can see that the condition number is found. Relatively small change in B is giving the loss and may affect the least square solution. Ma'am, but it's product. Yeah, so small Yeah. So if point 2 is multiplied by point 8, point 3, so it is giving you 0.6. Okay, means 0.002, because this is small, this is given you, and this is also small. So how it is affecting 0.04? This is also small, right? So from that perspective, it will be small. Yeah. So if let A belongs to Rm cross n and B belongs to R power n, the least square problem has a unique solution only. So as we know, what should be the answer? What should be the answer? Answer should be D, B and C, because as we know, the least square solution will have the unique inverse that was giving you A transpose A, whole inverse A transpose into B. Okay, this particular is which is a pseudo inverse, and using the SVD today we saw, that is um, that is what U sigma plus, this was V sigma plus U transpose. Okay, so when the columns are linearly independent, definitely it will be the same. And this is giving you the augmentation. Okay, since B lies in the column space of A only, so that's why the rank of A or rank of A by B should be n, means same. So that's why the answer will be D. Definitely the answer will be D. It follows from the definition. So what this C statement mean here? Okay, so if B, today only we saw this diagram. Uh, the diagram was there. Okay, if it is a column space of A, okay, if it is a column space of A, and if it is Y, and if it is this B, and if this is B, okay, and we only calculated the theta, this theta between B and Y, where Y is actually AX, when this B is not in the column space of A. So in that case, the unique solution doesn't exist. Whereas this this will be the second case where B is lying in the column space of A. So this will be the polynomial definition. Now, consider the linear system Ax is equals to B, where A is belongs to M cross N. X is this one. If the minimum singular value of A is very, very less than 1, the maximum singular value of A is very, very greater than 1, sorry, greater than 1, then how would the least square solution be affected by the perturbations to B? So again, following to the definition. So the least square solution is actually less than equals to K2 of A. Del B by B, writing in a proper way, del X by X is less than equals to K2 of A into 1 by cos theta del B by B. Now, since theta is not given here, K2 of A only we have to take care. So K2 of A is what? Sigma 1 by sigma n. If it is first component is it's greater than 1. If it is greater than 1, suppose 1.5. And if it is the sigma n, the least is less than 1. So let's keep it 0.2. Okay. So definitely this will be giving you more perturbations. A, yeah, because this exponent, this the fraction is more. So it may be more sensitive to perturbation, because yeah, again, this K2 of A is given by sigma max by sigma min, where sigma max is the largest singular value of A, where sigma min is the smallest singular value of A. And if we can see that under condition, if it is this, the small change, it will be affecting more to the least square solution, that is X. Okay. This is very great. What is the normal equation for least square problem? Normal equation means what? Multiplying by A transpose. AX is equals to A transpose Y. Because this is the range space or the column space. If you multiply by A transpose, I think the answer is T. Follows from definition of normal equation. Multiplying with A transpose will give you the more normal equations. Shit. So I think this week is very easy. I don't know what is the current week, but yeah. So what is the least square solution to the linear system Ax is equals to B, where A is this one, if rank is less than n. So definitely if the rank is less than n, so the columns of A will be linearly dependent. Okay, so what should be the answer? Are you sure it is B? So I'm giving you 2 minutes time. Can you please tell me what should be the answer of 8? Okay. So, so if the rank of a matrix is less than the dimension of a matrix, what does this mean? This means that the columns are linearly dependent. Okay. So if the least square, if you see the solution of this least square, this x is nothing but A transpose A whole inverse A transpose into B. So this happens, the least square solution can only happen to either tall matrix or square matrix. And we calculated this. Okay. Now this is the solution. If the columns of the linear of the matrix is not linearly independent, then what we found, the solution will exist, but it will not be unique. So the answer should be it is not unique, because it will have infinitely many solutions when the rank of a tall matrix is less than number of columns. Okay, so this is a well-known definition. So yeah, going to the ninth question. So this is again coming from principal component analysis. So which of the following statements is false? Any guesses? So first is PCA can be used to select the direction of maximum variance. Second is PCA minimizes the orthogonal distance of the data from the lower dimensional subspace. PCA can be used to reduce the number of dimensions in the data. PCA minimizes the vertical distance of the data from the lower dimensional subspace. So yeah, if you join my class, I think I told this so so many times. False, false. You need to tell false. So answer will be D. It doesn't minimize the vertical distance of the data from the lower dimensional subspace. It minimizes the orthogonal distance of the data from the lower dimensions of space, but doesn't minimize the vertical distance. So vertical distance is taken care by the least square. That is the difference between the principal component analysis and the least square. So if we revisit this, so PC is actually principal component analysis actually giving the data into 2 dimension or 3 dimension, that is based on the eigenvalues or the eigenvectors. So if it is 2 dimension given in V2, this is the direction of maximum variance, this is the direction of minimum variance. So that is taken care by this principal component analysis. The first statement is very, very true. This PCA can be used to select the direction of maximum variance, that is V1, true. PCA minimizes the orthogonal distance between the data and the from the lower dimensions of space, V2, that is true. PCA can be used to reduce the number of dimension data, very true, because number of dimension is n. You are representing in 2 dimension, that is very true. PCA minimizes the vertical distance of the data from the lower dimension space, that is wrong. This is the function of least square. So yeah, answer is D only. So this is the last question for this class. Any guesses? Yeah, I'm waiting. So question says that when does the linear system equation doesn't have any solution? Doesn't have any solution. Okay. Yeah. When rank of A is less than rank of AB. When rank of A is equals to rank of AB. When the rank of A is greater than rank of AB. Very true. Okay. So definitely when the rank of A is less than rank of AB, then we saw that infinitely many solutions exist. When the rank of A is equals to rank of AB, then a unique solution exists. When the rank of A is greater than rank of AB, definitely no solution will exist. So yes, the answer will be C. No solution. The answer is wrong here. Answer should be C. Because here only we saw that the rank of somewhere we saw, but the answer will be C only. That is for sure. When infinitely many solutions, when rank, yeah, it has infinitely many solutions. When the rank of the tall matrix is less than the number of columns, so definitely less than will have solutions, but greater than will not have. Okay, so okay. My problem. Okay, my problem only. Okay, so sorry. Answer is A only. So yeah. So rank here. This is a system of linear equation. That is A and B. X is equals to B. Okay. When is this case? When rank of uh, rank of A, B is greater than, this is a system of linear equation and this is greater than A. So it doesn't lie in column space. So this is the answer. But here, if it is greater than the rank of AB, then definitely it is lying in the solution, lying in plane columns. When can we have a rank of A is greater? That is a not possible solution. Yeah, it doesn't happen when the rank of A. No. This happens. This C is okay. This A doesn't happen. Because this is a system of linear equation. Suppose A is a matrix, okay, and you're augmenting with B. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Suppose this A, this A is having the rank of 3, suppose, and you are adding is 1 by 2, 3. So it is giving you the rank of total A, B is this one. So this is giving the rank of 4. If 4 is greater than A, rank A, obviously. So this can be the case. But rank of A can at most be equal to rank of AB, but cannot be greater than. That is correct. Correct. The rank of A cannot be greater than. Yeah, that is correct. No, it can be. So sorry. It can be. The statement is correct, wrong. Can be. How it can be? Let me tell you one thing. Uh, rank of A, suppose this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And rank of AB is suppose 1, 2, 8, 14. Okay. So rank of A by B का rank क्या है? Rank of A by B is actually 3. Rank of A is 3. Yeah, you are correct. This cannot be the case. Yes, yes. It can be at most, but it cannot be greater. Definitely, because you are adding. Ah, that is correct. Okay, this question was somewhat okay. So all of the questions are very good. They can go through. Okay, so I think that's enough for today's class. Um, we saw some of the concepts, then we saw the problems. Thank you so much for joining. Yeah. Okay, use backlog. So how many weeks you have was the lectures? Okay, that's fine. That's fine, Ravi. Even 6 weeks you have watched, no, that's fine. Because if you go to the seventh, eighth, ninth week, that is not at all related. That is not much related to previous weeks. You can watch. Because if you watch suppose Saturday, Sunday, if you watch all the lectures with 2x, then you can watch all the lectures. And if you don't want to watch the lectures also, the lecture material is given. You can read and you can go through. You don't have to prepare the notes. If you prepare side by side, then definitely it will take a hell amount of time. For practice, you just have to. I think the questions will be easy in the exam, even if it is not. So if you do all the questions of already this previous year, which I am telling you, and other TA is also telling you, as well as this year properly, because anyway the solution is also released with every week. Okay, so even if you do if you do all those 2 weeks, so previous year and this week, so you can easily get 80% of the marks. Definitely 80%. But if your concepts, even if you because if you are solving all those questions and you are watching all the lectures, then you can definitely get 95% of the marks, provided you have some enough marks for the assignments. That is only 25%. Yeah. Okay, so thanks for joining.